Okay, and now it's time for 7.8 lecture, what amounts to number 4. You had 3 lectures last time, including that little interesting tidbit about the Haber reaction. So we're going to just kind of continue where we left off on the last video. So we'll finish this up, and then I'll post the answers, and you'll be able to finish up the assignment. The next problem involves a little bit of knowledge about the pH scale, and I'm going to assume that you guys have a good knowledge of this, that a low pH means very acidic. So in terms of the hydronium ion concentration, that would be very high down there. If it's a high pH, very low concentration. Because you can think of these loosely as being negative exponents, and they get smaller and smaller concentrations as you move up in terms of the hydrogen ion, which basically is the same as the H3O+. Okay, so that allows us to do a reaction where we have a weak acid like this in an equilibrium system, and this is the part that's going to change the pH. If we get more of this, pH is going to go down. If we get less of this, and it shifts there, then the pH will go up. So here's using Le Chatelier's principle in a sort of contextual thing with acids and bases, kind of leading us into our next unit. But you need to know what a temperature change is going to do to this. When you increase temperature, you have to know where the heat is in the reaction. So remember, it's endothermic, so it's going to be over here with the reactants. So you're adding heat here. That's going to shift to the right. It will shift to the right because the heat is over there. You add and it goes away. Add, it goes away. Take away, it comes back. But we're going this way. All right, so we're adding heat, and it will proceed in the endothermic reaction or direction. You can memorize that if you want. I prefer to use the conceptual stuff. Just endothermic, the heat's over there, and when you add to that side, it'll go to the right. And of course, this would cause an increase in pH. I'm sorry, a decrease in pH as the H3O plus goes up. Okay, you get a stronger and stronger acid. That pH goes lower and lower and lower to, it can even go off the bottom of the scale. I don't know if you knew that. And the top of the 14 scale as well. That's kind of arbitrary based on humans and biological systems. So anyway, that allowed you to apply Le Chatelier's principle. There's the Haber process again, saved us from starvation. This one is an exothermic reaction, so you know the heat is on the product side. Now, this one's kind of cool what they did here. So you have a set temperature, and now you're going to take the volume of the cylinder and you're going to increase it. Now remember, that has to be like a closed system, something like this. So you're going to increase that volume, all right? And when you increase the volume, then it goes to the more crowded side, which is the reactant side, okay? So when you increase the volume of this system, it's like a spring bouncing back. It goes back to having more nitrogen and hydrogen. So remember, the heat is over here as a product, so you're taking away heat as you go, and you had to know, which side the heat was on, because when you're driving this left, the heat is going down, and a decrease in heat most times involves a decrease in temperature as well. Okay, so I'm guessing that the temperature would decrease because it is a exothermic reaction and you'd be pulling away from that heat on the right side. Shifting to the left, and the reverse reaction is endothermic. That's another way to think about the temperature too. If you're going this way, it's endothermic because you know it's exothermic going that way. That's a good way to look at it as well. All right, now let's do some crunching of numbers with some of these things and apply Le Chatelier with something we did last lecture. Okay, not the beginning of 7.8, but 7.7, where we talked about those ice boxes. Okay, so here you got 80% nitrogen, 20% oxygen. So basically, air is what you're looking at. Okay, and it's a pressure of 1 atmosphere, and this reaction between nitrogen and oxygen, it looks like it's not very favored. Well, thankfully, because our air is nitrogen and oxygen, and at that temperature you don't want it turning into that nasty nitrogen monoxide. Okay, so and it says find the initial partial pressures of each gas. If you have percents and you have the total atmosphere, that's a pretty straightforward. You just take and tell what you're doing on each one. So just say P sub N2, or you can write the partial pressure of nitrogen gas. I prefer this little formula. Tells a lot, doesn't it? 1.0 atmospheres times 0.8, that's your percent, and that is your partial pressure of nitrogen. Basically, on your average day, that's going to be your partial pressure of nitrogen in the atmosphere. Partial pressure of oxygen, about 20% of the air. So this one, it's a pure sample because we're really going to do some specific numbers moving forward on this. All right, so now we've got the partial pressures, and of course, at the beginning, no NO has been introduced, and you haven't allowed any of the nitrogen and oxygen to react, however small that amount may be. So, if you're going to talk about these things intelligently in an equilibrium problem, you know that you've got your initial, and then it's going to change, and then you're going to be at the equilibrium, so you use the ice box. And you plug those in, and again, use the balanced equation right there is just fine. You could write that in your ice box or at the top of it, or even just jump right into the ice. Just remember that the C also stands for coefficient. It's the change, yes, but also you can use that as representing the coefficient. So you can see here minus x, because they're disappearing on this side, and then you get the plus 2x on that side, and then you just combine the initial and the change to get these little equations, and that's what you can now plug into, boom, the Kp, so you'll be using parentheses. That's an important little detail, so make sure that you get that right. And you end up with the products squared on the top, and then the multiplying the two reactants on the bottom. So you can see here, this has the potential to be some kind of challenging math, which we will do on the next problem. So hang in there. This one, K value, our Kp value, was so darn tiny. This reaction, the forward reaction, just doesn't happen very much. So it is an okay thing to assume that if you're subtracting, it's very important that you know. That's why we can do this little cheat that we've been doing, and today and yesterday's lecture. You can do that because you're subtracting, and this will be off the charts small. So this is going to stay 0.8, and that's going to stay 0.2. It'll have no effect on it. So You can go ahead and write that in there if you want, because remember our cutoff point was less than 1 times 10 to the minus 4th. Then we can ignore it. So really small KP, you're just plugging that in. You're just doing a little math to clean that up. Multiply those two, you get your 0.16. Crunch the numbers in your calculator, and you get x equals 2.0 times 10 to the minus 16th. Now, what does that mean to us here? Well, that means if you were trying to find this NO, it would be 2 times x, all right, which is 4.0 times 10 to the minus 16th. Easy math there. The nitrogen and the oxygen, 0.80, 0.20. Now we know in our hearts that these are both slightly smaller, but there's no way you could justify going that many decimal places out. So so they stay the same, and that's why you can avoid using the quadratic formula. I know that sounds horrible, doesn't it? Okay, now this problem is going to involve the quadratic formula, so I'm going to let you stop this video, because this will be on video number 5. We are going to do this problem where the math is just a little bit more intense, and I do not want to be rushed, and I'm at 11 minutes and 37 seconds. So we are going to just do part C of this, and you can see KP is not so very small in this instance. Okay, they probably changed the conditions for that. All right, so we will attack this problem on the next and last video of this particular section of equilibrium.